And now I'm going to talk about superconducting qubit. It is the most promising in terms of technology maturity. So now Google, IBM, they all have more than 500 qubit system, which works well, and they also try to do error correction. So we will follow what we said at the beginning to look at the 5 criteria to make a successful quantum computer, right? Two-level, it has to have two-level system, long coherence time, have one universal set of gates. You can initialize it, you can read it, which Dr. Bashir already mentioned in the silicon qubit system, right? Except we did not talk about the 2-qubit. I'm not a circuit engineer, I'm not circuit expert as he, so I will go from a higher level. I won't go to, but for superconducting qubit, we also don't need to go to so deep. But you will see a lot of things that are similar to what he has mentioned. So how can we form a qubit in superconductor? It turns out that if we have a LC resonator, an inductor plus capacitor, we know that it has a resonant frequency. And we need to remind ourselves, electromagnetic wave is very general. So a photon is also electromagnetic wave. When we say a resonator is at resonant frequency, it means that it captures the energy of a certain frequency of electromagnetic wave. Now, if we cool down the resonator to very, very low temperature, you can imagine there will be quantization. At the extreme case, we can say that we can store 0 or 1 photon in that resonator, right? Remember, because the resonator at resonance is just the electromagnetic wave of that particular frequency. So when we keep lowering the energy and also put it at very low temperature, it's possible to go to the minimal energy, which is with 1 photon or with no photon, right? So that is what we need to look at this problem when we talk about the LC tank at very low energy. Now, in that case, if you solve the equations, just like what we did in simple harmonic oscillator, the mechanical simple harmonic oscillator, if you have not learned that before, it's fine, we take it for granted, but you have learned the quantization of a simple harmonic oscillator before, you probably remember we promote the position, the coordinates, and the momentum to an operator. And we say position and momentum are conjugated pair to each other, right? Based on Heisenberg uncertainty principle, basically, based on Heisenberg uncertainty principle, you cannot measure them accurately at the same time. But anyway, the message is that if I do the same quantization, go through the same math for a simple harmonic oscillator, for an LC tank, just inductor and capacitor, I will have this quantized level, just like a simple harmonic oscillator, right? Let's take it for granted. But the important thing is that now instead of position, we actually have the flux as the so-called generalized coordinate, and with the charge as the generalized momentum. We also take it for granted, just let you know that it's parallel to what we're doing for a simple harmonic oscillator. So we have equally spaced level from the ground state to first excited state to the second excited state, keep going up. Now, is that a problem? I have 2 well-defined levels, definitely. But the problem is the separation between adjacent states are the same. From ground state to the first excited state is same as from first excited state to the second excited state. And again, what is a quantum gate? If I shoot, it is a microwave pulse or a laser pulse. So if I shoot the corresponding energy, then it means that besides I can bring it from the first excited state to 0 to the ground state, it's also possible to bring it to the next excited state. So this is not a good qubit. And we say that it is lack of anharmonicity. Anharmonicity refers to the fact that we want them to have different spacing. If I have different spacing, then I will more confidence I can confine the qubit at the 0 and 1 state that we mentioned in this morning, right? But this is a very instructive exercise because based on that, we will think of a way to make it work. But before we go further, let's just quickly talk about superconducting. What does it mean, right? So when the metal goes below its critical temperature, the electron will pair together, form the so-called Cooper pair. Now, the Cooper pair have opposite spin. So instead of being a fermion, like what it was mentioned in the spin qubit during the readout, now they become a boson, just like the light, that you can put all the particles at the same state. So what does it mean? I can put 10 to the power 23 electron in per cm cube. Cooper pair per cm cube. They share the same phase. They share the same amplitude, just like the laser. We can never make electron laser, but we can make photon laser, right? Now, of course, we cannot make Cooper pair laser also because it only exists in solid state, right? But the main point is now I can describe this macroscopic quantum object because it's very big now. You have a lot of Cooper pair with a simplified wave function. This is the wave function with the amplitude and also the phase, right? All of them share the same thing. And here just a hand-waving argument on why the electron will pair together to form a Cooper pair, because they are both negatively charged. They should repel each other. That is because of their interaction with the lattice. The blue dots are the lattice, the positive atomic nucleus, right? And then the red are the electron. Now, when we have an electron here, it will interact with the lattice, so pull them a little bit closer together. So in this region, the density, the charge density is a little bit more positive than other region. And as a result, this will attract the electron to there. So some people will think about the mattress that we sleep on. You push it down, then you form a slope, then the ball will go to there, right? So you can think in this way. But this is a good instructive material because it means that you need electron and atom vibration interaction. So the Cooper pair formation is a result of the interaction between the lattice and the electron. And that's why sometimes you need a bad you cannot make a good conductor like copper to be a superconductor because they don't have enough interaction between the lattice and the electron. Okay, but in summary, maybe I say too much. The main point here is that at one terminal, the metal at the superconducting state, it became a macroscopic object described by one phase. Okay, then we come up with something called Josephson junction. So what is a Josephson junction? It is just a superconductor, insulated superconductor. After all, it's just a capacitor, except that we cool it to very low temperature, but with these two terminals being superconducting. Here shows a cross-section of how people mix Josephson junction on integrated chip. We have a high-resistive silicon substrate. We deposit the aluminum, oxidize it, and then deposit another layer of aluminum. Now, this aluminum is actually pretty thin, but it's not too thin. So there will be some interaction between these two, the wave function in these two aluminum. We just said that in a superconductor, all the Cooper pairs form a macroscopic quantum object. So they have a single phase. I call it phi A at this side. And then in another electron, it is phi B. And it turns out that Josephson junction gives two equations called Josephson's equation. First, the current passing through this junction is proportional to the sign of phi, of the difference of this phase, phi A minus phi B. So if there's a phase difference, remember this phase refers to the phase of the wave function, the phase of the quantum object, which you cannot measure directly. It's just the phase, right? It is the sinusoidal of this phase difference. So what does it mean? If I have zero phase difference, I have zero current. If I have finite phase difference, then I have finite current. It's not that surprising now. Another equation tells us that now if I apply a voltage across this Josephson junction, the phase will change as a function of the voltage. If I have a constant non-zero voltage, the rate of change of this phase is non-zero. So basically, it means that I apply a constant voltage across A and B. Remember, it's constant. Then it means that the phase will change as a function of time. If the phase keeps changing as a function of time, it means the current will oscillate. So now a constant voltage across Josephson junction gives me an oscillating current. That's what you will not get in a classical or normal metal, right? That is the special thing about this. And all these things eventually give us something very interesting. It has inductance, the Josephson junction. And its inductance is nonlinear because the total inductance besides is related to the Josephson inductance Lg, which is a constant, depends on some constant. It also depends on the cosine of the phase difference. This is the first thing. And second thing is that if you have inductance, it means I also store energy. You can go through the derivation and you find that, again, it has the Josephson energy, which is the inductive energy. It will be interesting to discuss the nature of the inductance, right? In RF circuit, the inductance is referring to the magnetic field it established in the air or in the surrounding and store the magnetic energy. And the inductance is the inertia. You try to resist the change of the system because you have the energy stored. But here we don't have any magnetic field. The inductance is something called the kinetic inductance, which means since it is a superconductor, the electron will just keep running. It doesn't stop. So that is the inertia of the system that it has. And that is the inductive energy it has stored. So even for a normal metal, we have kinetic inductance. But because of the generation of the heat, the slowdown of the electron due to friction, the resistivity, so they are not important. The main point here is that we can create very large inductance with a small geometry with Josephson junction. And we'll see later in the tape out. Okay? So the main message here to take home is that Josephson junction provide a nonlinear inductor. And why this is important? We have this enharmonicity, a lack of enharmonicity was because we have a linear inductance in this LC tank. Now, what if we replace it with the Josephson junction? So this is the symbol of a Josephson junction. The cross refers to the, you can say, the primitive part of the Josephson junction that give you this Josephson equation. But this is a capacitor. Of course, it also has a parallel capacitance, right? So this is the symbol of Josephson junction. Now we replace this Josephson, the inductor, the linear inductor, geometric inductor, with this Josephson nonlinear inductor, and put it in parallel with the capacitor. So originally, we have this parabolic potential well in the LC tank. Now with this nonlinear inductor, you will give something actually with enharmonicity, which is actually sinusoidal. It actually has a cosine term. If you look at here, but we don't need to go to detail. Basically, this is periodic. And because of this, naturally you will think that if you solve the equation, the separation of the levels won't be constant anymore. Very common, the first separation will be larger than the rest of the separation. So with this, we then successfully create a qubit with two well-defined levels and also with low probability to be excited out of the Hilbert space, that is the 0 and 1 states that we are interested in. Okay, and we talk about the so-called enharmonicity is the difference between E21 minus E10. And this E10 is the qubit frequency, or the frequency we call the Larmor precession mentioned earlier in the spin qubit. Okay, so now we have a well-defined two-level system. We fulfill one criteria of the differential criteria, right? But if you go, if you look at the literature, people nowadays, they will talk about the Transmon qubit. This Transmon qubit is actually just the same as what we have discussed, but it operates in a special regime. So why they want to use Transmon qubit? So Transmon qubit is that in parallel to this Josephson junction, we add a large shunt capacitor to it. So they are in parallel. With a large capacitor, because the capacitive energy equals to half Q squared over C. So if you have a large capacitor, you have a smaller capacitive energy. So again, the Josephson junction is just like an inductor. Or we can say it is the energy of a Josephson junction energy, but in some sense, it's the inductive energy, right? So we make a large shunt capacitor, we will make the capacitive energy much smaller than the Josephson junction energy. Why we want to do that? That is because if we don't have this shunt capacitor, in this graph, we plot the qubit level. Now, this is the qubit energy. So level. So this is the ground state energy. Let's say this is the ground state energy. The orange one is the excited state energy. At the bottom, we put the background charge, Ng, right? Because this system is coupled to the outside environment. So there will be a background charge presenting to this system. You can have 0 background charge, or you have 2 units of background charge. And you see that the energy of the first excited state actually change a lot when the background charge change. This is the primitive charge qubit. And that means it's not good. Because if I have a little bit noise coming from the environment, right? Maybe the car just moved by, you generate some noise, then my qubit frequency will change. And qubit frequency is related to this one, which is the Larmor frequency we just mentioned this morning in the spin qubit. It changes the precession rate. So that means you have a lot, very sensitive to noise. And that's why people add this capacitor. If you have a small capacitive energy, you see that it's very flat. It's independent of the background charge. So it's very insensitive to the charge noise. But there is a trade-off, of course. Now, you look at the enharmonicity. Look at this point, for example, if I have this background charge. E10 is very small. E21 is very large. This is a very big enharmonicity, which we want because we then can confine at this two level very well. But here they become closer to each other. But luckily, they are still not too close. They are still good enough to keep this as a two-level system. Because charge insensitivity goes down exponentially with the ratio of these two energy, while the enharmonicity goes down in the power, how to say that? Yeah, power instead of exponentially with the ratio of these two energy. Right? So that's why Transmon is the most popular qubit being used by IBM and Google nowadays. Of course, they have more variation, better engineering, but this is one of the basic. So now we have a good system. We have two level, and we also have it pretty insensitive to the charge noise. Then how do we implement the single qubit gate? So let me just remind you again, right? It was also mentioned this morning about the broad sphere. What is a single qubit gate? On the surface of the broad sphere, every point matched to a state of the qubit. So the operation of a qubit of a gate is nothing but just moving the state on this broad sphere from one point to another point. And this is like you can prove by Euler rotation or equivalency that it is no matter where you want to move from or move to, you just need to do free rotation. First about this z-axis, and then rotates about this y-axis, and then rotates again about this z-axis. So you only need three parameters, theta, phi, lambda. Then you will be able to move from any point to any point. Then it means if I can implement the rotation about this three axis, then I can implement any single qubit gate. Okay. Now, another reminder is that we talk about the universal set of quantum gates. If we want to implement any quantum algorithm, right, there are two possible sets. I mean, there are many. Two of them we highlighted here, but they all have the same requirement. One is that we need to have the 1 qubit gate be available. Another is you need an entanglement gate, which is 2 qubit gate. Here we're talking about 1 qubit. We'll talk about 2 qubit later, right? So finally, then we say that we need to be able to do the rotation about any axis, okay? So the rotation about any axis turn out to be the exponential of this Pauli operator, which we will not go into detail, but let's just take it for granted that as long as I can create the Hamiltonian to which is depends on sigma x, sigma y, sigma z, they are the Pauli matrix, then I will be able to rotate my state on the Bloch sphere to any point. Why do I want to say that? Then now I want to let you take a look how we implement a Transmon qubit single qubit gate. This is the Transmon. Again, this is the Josephson junction. This is the shunt capacitor to make the whole thing charge insensitive. So it is a two-level system. All we need to do is just capacitively couple it to a voltage source. And then I will generate a voltage source in the frequency of omega 1 with the envelope of ST. So remember this morning we say that we need to send the right pulse with the right shape, right time, right amplitude. Frequency is just the carrier, but it's also the right frequency. S of t determine the right envelope, right shape that you want to do so that you can change the state of this qubit, right? Of course, because of time, we are not going to derive them. It's meaningless to do so, right? The book coming up with derive it step by step. But if you go through the derivation, you will see that the Hamiltonian, what is Hamiltonian? Hamiltonian is the energy of the total system. And it's not difficult to understand that your object will evolve based on the energy, right? You put a ball on a hill, and of course, it will roll based on the slope of the hill. And if there's a valley, or it will go up again, because you set up the energy landscape, you set up the Hamiltonian, then the state of the system will evolve according to the Hamiltonian you set up. So it's the same here. I set up the landscape, then I get this Hamiltonian. Let's look at this Hamiltonian. First, I have omega 0. This is just the qubit frequency, E10 that we mentioned earlier, this one, okay? I also have H omega R. What is omega R? Now, if you look at this, it depends on the shape of my pulse, the envelope of the pulse, S of t. It also depends on the capacitance of the coupling capacitor. It depends on the total capacitance, including the junction capacitance, shunt capacitance, and also the coupling capacitance. It also has a quantum fluctuation point, which depends on some fundamental constant. But my main point here is that this one related to the circuit parameter that I have set. Now let's look at this Hamiltonian one more time, right? You find two things. One is sigma z, one is sigma y. When you see these two, maybe you don't know what it is. But let's look back at this slide again. You see that if I am able to generate a Hamiltonian with sigma x, then I am basically rotating the qubit about the x-axis. If I can generate sigma y, I'm rotating it about the y-axis. If I can generate sigma z, it will rotate about the z-axis. So with this, basically, I am able the qubit up on the Bloch sphere about the z-axis and also about the y-axis at the same time. And how much do I want to rotate? All depends on how long I apply this pulse and what is the shape I applied. Is that okay? So here show that you can use the circuits to control something looks like quantum mechanical. Now, this is not convenience, but originally we can just stop here, but it would be good to just say a little bit more. But we don't operate qubit in this way. You often will hear about something called rotating frame or rotating wave approximation. So what does it mean? This one, although looks okay, but only allowed to rotate about y. That is not enough. We want to have more flexibility. We want to rotate about the x also. So without derivation, we can show that if we work in the rotating frame, it means that now my whole system is just a mathematical transformation. Instead of looking at the qubit from a lab frame, I try to work together with the Larmor frequency because it is rotating about the z-axis, just like the merry-go-round. Instead of standing outside, now I jump on top of it and measure the physics. And now then it becomes, then we say we are working in the rotating frame. With this rotating frame, then we add something called rotating wave approximation. Then I will be able to come up with something more elegant, right? And what is rotating wave approximation? So this superconducting qubit, although up to now we have not seen any magnetic field, no real magnetic field, it's not the spin case, right? And the so-called inductive energy is just the kinetic inductance, right? But if you go through the math, it has exactly the same formulation as a spin qubit with a magnetic field oscillating in the y direction. If I have a magnetic field oscillating in the y direction, I can decompose the oscillating magnetic field as two magnetic fields. One is rotating in the anti-clockwise, another is rotating clockwise, right? Because when both of them rotates to here, the net magnetic field will be 0, right? If we both are pointing in this direction, it will be 2x. So if I do that, and then I also go to the rotating frame, I follow one of them, which is the rotating the merry-go-round. Then I will only feel this one because the other one is leaving me very quickly at 2 omega. So you can imagine if someone tried to push me to left and right, but at very high frequency, I would just stand still because before I can react from the push from the left, he already pushed me from the right, right? So that is the so-called rotating wave approximation. So maybe a little bit complicated. I did not explain it well, but the main point is this, is very often you will see that people say we try to work on the rotating frame. By working on the rotating frame, it means that you go to the frame of the qubit frequency or the pulse frequency so that you can make it more mathematically simpler. And then you also have something called rotating wave approximation, in which you ignore those high frequency components. And everything becomes very elegant. With that, if you try to map to a spin qubit, I should be SPIN, a spin qubit under a rotating frame, they will have exactly the same physics. And basically now with sigma x and sigma y, it is equivalent to say that I can create an axis on this plane in any direction. And then my qubit will just rotate about that axis. So I can do any 1 qubit rotation as I want. And that is how we achieve the single qubit gate in superconductor qubit. Okay. But very important to remind yourself, actually, I forgot to say one thing, and remind yourself this omega r, what is that? Again, it depends on the envelope of the pulse and also the electrical element. We also have this I and Q, and what are they? It is just the cosine phi. And what is phi? It's just the initial phase of the pulse you shoot to the circuit. So you see that now I control the rotation by designing the initial phase and also the envelope of the pulse I want to use. Okay, and later we will see how to synthesize that. So now we know how to do 1 qubit gate. Then how about 2 qubit? We need an entanglement gate, but we cannot use C0 gate because the physics of superconducting qubit does not allow us to implement the C0 gate easily. And so we say that it's not the native entanglement gate. There's something called I swap gate, and this is its matrix. It has a swap operation. This is native to the Transmon qubit. So how does it work? Again, a lot of math. We don't need to know exactly what it is. The point is, I have 2 qubit here. Again, you recognize this is a Transmon qubit because this is a Josephson junction shunt with a capacitor. This is another Josephson junction shunt with a capacitor. They are capacitively coupled to each other. Now, in the normal operation, remember, this is a fixed device. We cannot break them or connect them on the run. They are just the integrated circuit. So in the normal operation, we will make the resonant frequency of them to be different. So they can be addressed differently. They are working as 2 independent qubit. But when we want to do the 2 qubit operation, what we do is we will I need to step back again. However, we may at least make one of them first tunable. So here I did not show that, but a first tunable qubit is a qubit that its Josephson energy depends on external flux. If apply a magnetic flux to that qubit, you will change the total Josephson junction energy. It is like a squid, but with 2 Josephson junctions. Here, I just lump it into one single Josephson junction. A first tunable qubit is like a squid, like superconducting loop that you pass the flux, and then you will change the effective Josephson junction and Josephson energy. By changing this, I will be able to bring its frequency to be the same to the other one. Then resonance will happen. Okay, so I did not explain how we change it, but please trust me, it is that we need to do something to bring their frequency to be the same when we want to perform a 2 qubit operation. Okay. And if you go through the math, you see all this, again, it's meaningless, right? If we don't derive it. But we want to highlight a few things. First, again, I have RF. We're working on the rotating frame. It's very often you will see this. Right, this is Hamiltonian in the rotating frame. We are following the qubit frequency of each of them. But you see that the interaction depends on something called G, which is the coupling factor. And this G, if this G is 0, then it means there's no coupling. Then you don't have 2 qubit gates. So it means this 2 qubit gates depends on G. And what is G? G depends again on CC, the coupling capacitance. The individual C capacitor of the Transmon, and also the square root of their frequency, right? So I actually can decide the strength of the coupling by changing the capacity, the circuit element. I also can influence it by designing what the Josephson junction energy should be, right? So with this Hamiltonian, then we go to Schrödinger equation, then you're going to evolve as this matrix. What we need to do is find a time so that this becomes I and this becomes 0. When the time equal to 3 pi h bar divided by 2g, then we have the I swap gate. So basically, that's what you will do. First, you design the circuits with the right parameters so you have the right G that you want. And then when you're operating it, you change the resonant frequency of one of the qubits to bring them to be the same. So they start interacting for a given time. The time is such that it's equal to 2 pi h bar divided by 2g. And then you turn it off again so they don't interact. And through this period, they already finished the eye swap operation. Okay, so again, it's the right pulse, right shape, right time, right? So very important high-speed control is required. So if we have eye swap gate, then so what? Here, just to show that with 2 eye swap gates and many other 1 qubit gates, it will be equivalent to a CNOT gate, right? If one has time to go through all the matrix multiplication, you will see that. But again, remember, what does this mean? It just means that I need to apply 2 pulses to 2 qubit individually. Right? The first qubit get this rotation gates pi over 2. The second qubit identity gates don't do anything. And then after a certain time, I apply a rotation C gate, the top qubit by pi over 2, the bottom qubit by negative pi over 2. And then I try to do the eye swap gate by bringing them to resonance for a certain time, and then bring them off. And continue this, right? Again, I'm not laying out the circuit. I just apply the corresponding microwave pulse. And then I implement the eye swap gate. So with this, cool, then we are done with the 1 qubit and 2 qubit gates, and we can implement any algorithm from this point onward, right? Although whether it's efficient, that is another matter. Okay, now, so we now have a well-defined 2-level system. We have the universal set of quantum gates, but how do we do the measurement, right? But no, actually, I need to continue just to talk about the manipulation also. So exactly what usually nowadays, how a superconducting qubit system look like. These are the room temperature high-speed electronics, FPGA, Python programming, arbitrary wave generator. We can create microwave digitized pulse, megahertz or some megahertz high fidelity digitized pulse easily. That is the S of T, the envelope function we mentioned earlier. Then we go through the mixer to bring it to high frequency to gigahertz. Go through all this attenuator from room temperature, and then eventually we reach a resonator. This resonator is coupled to a qubit. You also can just capacitively couple this one to the qubit to do the 1 qubit gate. If you're doing the manipulation, you are done. You send a pulse, the wave function change. But if you try to do the readout, you will try to measure the output from the resonator. And then based on the output, you can determine whether it is 0 or 1, which I will discuss later. But the signal, of course, need to get amplified on different stages, and then eventually down convert to the megahertz regime so we can analyze it, right? So the whole superconducting qubit is really just one boring passive Transmon qubit here. The rest are just the exciting programming, controlling, cryogenic, electronics engineering, electrical engineering, right? So let's see how we do the 1 qubit gate. The purpose is to generate this Hamiltonian we mentioned earlier. And we already say that if I can generate a wave that is S of T sine omega 1t plus phi, then I will be able to get this Hamiltonian. We did not derive it, but I showed that, you trust me, that is the result if we work in the rotating frame. So now it's very easy. This part becomes just purely electrical engineering, right? Just to make up the math, I have something a little bit weird in all this notation, but you will just give the right thing. For example, in the I port, the in-phase port, we generate this signal, 2s of t sine, and then a certain frequency, AWG. We can synthesize this easily, right? It's in the sub-megahertz regime. And the Q port, I generate Q. Again, Q is the sine of phi, and I is cosine phi, the phase, right? So here, basically just saying that I use this I, just a magnitude at this stage as the phase. And they go to the mixer, and this is a LO with a pi over 2 shift. Again, I just want to make up the math. That's why it's negative pi over 2. It's the same. After the mixer, you add them together, you will get what you want. Right? So nothing special, right? It's all math that we are not deriving here. But the main point is that to get this wave function, I just need the mixer with the right frequency. And then here, I just digitally synthesize all these things. And the amplitude of this digitally synthesized curve contain I, which is related to the phase of the final wave. And this phase is going to control how much rotation I have about the x-axis and y-axis. Right? In summary, I can determine how much it rotates about x and y by just changing the amplitude of this signal. So we are done with the manipulation. Then how about readout? So here show an example, a possible readout. So it is a transmission line. If I have a signal going in, it actually will get blocked unless this resonator is resonant with the characteristic impedance of this transmission line. Let's say 50 ohm. This is also at that particular frequency, right? So if I sweep the frequency, most of the frequency, I cannot transmit any signal. The S21 will be very small. Only when at the frequency this one resonance, then I will be able to transmit the signal from left to right. Right? So I will expect something like this, right? If I sweep the frequency. Correct? Now, then how do we measure the qubit? It turns out that just because of physics, we won't prove here. It's just like the so-called cavity quantum electrodynamic. You put an atom in a cavity, the resonant frequency of the cavity will change based on the states of the atom, whether it's excited or at ground state. And it is same here. I have a Transmon qubit capacitively coupled to this resonator. The resonant frequency will shift based on the state of the qubit, whether it is at 0 or 1 state. In this example, if it is, let's say originally, the resonator frequency is here. If the qubit is at excited state, it will shift to the left, the resonant frequency. If it is at the ground state, it will shift to the right. Now, if you try to just shoot a pulse at the resonant frequency of the original frequency of the resonator, you will get the same magnitude. You cannot distinguish, right? If this is so symmetric like this one, you don't know whether it's at the ground state or excited state, 0 or 1. However, we will measure its imaginary and real part. If you decompose the imaginary and real part, the blue is for excited state. The real part is the solid line, and the dash part is the imaginary line. You see that when it is at excited state, right, the dash line is about 0 when it is at omega r. For ground state, the green dash line is also about 0 when it is at omega r. But for the real part, the excited state is negative. The real part is positive. So based on this, you can think that, hey, I just measured the transmitted signal. If the real part is positive, then I know it is at ground state. If the real part is negative, then I know it is at excited state. And basically, this is just measuring the phase information of the transmitter pulse, right? So this is something called measurement using the dispersive shift of the resonator. And the difference of this frequency is called the cross curve. This is a very important engineering problem in superconducting qubit. You want to have enough separation, otherwise you won't be able to distinguish them. So the cross curve need to be large enough. Now, If everything is ideal, then if it's at ground state, I will get positive real part. If it is excited state is negative, right? So I just measure it. I see negative value, I say this is 1. I see positive value, I say this is 0. But in reality, you have noise. When you have noise, you can imagine that this will fluctuate because of the noise. So when you do the measurement, you actually have a distribution about these 2 points. It is also very common that people don't plot it in this way. They do some transformation, plot it like top and bottom, and plot it on so-called the IQ plane. This is in phase, this is conjecture, which related to the microwave signal we are processing. But the microwave signal, again, is just related to the phase, right? That's how they call it. So when you have noise, this circle will get larger and larger. Or if your cross-cut is not enough, the dispersive shift is not enough, they will get closer and closer. Now, once you touch each other, then you have a lot of readout noise. For example, if I find a point here, it has certain probability this is actually a ground state. It also has certain probability this is really the excited state, right? And that is the readout noise that one will get if you don't have the right design. So how do we get this IQ block, right? So it is just the inverse of the manipulation pulse generation. So here represent what goes out from the resonator, right? We shoot into the pulse, and then now we go back to the amplification train. So what we do, again, I just make up the math. With this system, I generate a 2 cosine omega 1t with this modulation, right? And you go through the math and go through a low pass filter to remove the high frequency part. Then you see that the Q port will receive A of t sine phi, and the I will become A of t cosine phi. So again, we get the phase information and also the amplitude after this demodulation. And that is how we plot. We get the plot from here. Okay. So let me quickly talk about the amplification. If you remember, we have a train of amplification. I said that everything is classical except the boring wave function. But actually, I missed one thing. We also have a quantum limiter amplifier. This is also quantum mechanical. This quantum limiter amplifier means that it adds the least possible amount of noise to the signal you amplify. So let's just go back that we have learned something. I assume you learned that it's called noise figure of an amplifier. So if you have a signal, no matter how small it is, you can hear if there's no noise. So what matters is not about the size of the signal, it's the signal to noise ratio, right? If you guys start talking, I need to speak louder, then you can hear me. Now, the amplifier will amplify the signal, but you will also amplify the noise. But in that case, you should keep the signal to noise ratio the same. However, amplifier is a physical object. It has a lot of transistor, resistor inside. You will add additional noise to it. So actually, you degrade the noise to signal ratio after the amplification. There is a law called Fitz's law, and that's called noise figure. And Fitz's law says if you have an amplification train, the total noise figure, it means the total effective amount of noise you add to it after amplification, depends mostly on the first stage noise figure. So that's why we want to have a low noise figure first stage amplifier in the train. Or in other words, we want to add an amplifier in the first stage where the amplifier has injected the least amount of noise to the signal, right? It keeps the signal to noise ratio as high as possible. And what is that? Theoretically, the best one is a quantum limiter amplifier. You cannot design an amplifier that does not add additional noise to your signal because of quantum mechanics, because of Heisenberg uncertainty principle. So people mathematically prove that. So this is just something I want to highlight. Because of time, maybe I will not talk about the parametric amplification. This is just to explain what a quantum limited amplifier such as Josephson parametric amplifier does. But what it does, I mean, I won't talk about the classical example, but here just tell you how it works. So you have a signal coming in. It goes through the circulator. Circulator, basically, you direct the signal to go around this circle. You cannot go back. And then you have a Josephson junction. Again, why Josephson junction? Because it provides non-linearity. So this forms a square root, and this is an inductor. If you have a flux that is 2x the frequency of the signal, it helps to mix them together, and somehow it can increase the signal strength of the incoming signal. Okay, and this just like the swing, right? Maybe swing here is similar to that. When you're playing the swing, you need to stand up and down 2x the frequency of your swing frequency. And that is called parametric because you're actually changing the parameter of the swing. Because you go up and down, you're actually changing the centroid or the effective length of your swing, right? Or the center of mass of the swing. As a result, you were able to amplify the swing. This is something like that, right? So I'm done with talking about what a superconducting qubit is. We know how to do readouts. We know, I did not talk about resets, but initialization is simple. You just thermally wait it to thermalize to 0 state, or you can measure it. If it is 1, you apply a pulse to it to reset it to 0. If it is 0, then you do nothing. That is something called active reset. We have 2 levels. We have the qubit state. We did not talk about the coherence time because it's too much, but we know that you need to limit it to a certain time, right, for the gate operation. Now, how about let's talk about how to design, not really how to design, just show you what are the tools or some of the electrical knowledge we have learned that we use in designing a quantum chip. And you find that I don't need to use any knowledge in quantum mechanics. Any electrical engineer can do that already. I don't need to use the knowledge just because someone already built a Python package and we will just extract the thing we want, right? But it needs our knowledge in electrical engineering. So Qubit metal is a very handy tool. Now, if you do IC chip design, you use Cadence, Virtuoso, or Synopsys, right, to do the layout of this thing. So what does this look like for Qubit metal? Let me show you. So I already started the Jupyter notebook, not yet actually, and I have a cheat sheet. So for example, I first will start Anaconda. I already set up an environment, right? You need to install the corresponding package. Then I will type Jupyter notebook in this environment. Then you will bring up the machine. And here I will make sure that I have the right port 888. Right. So you bring up something, but I will just open. You just go through the, right? Okay. Here I just try to be fast, so I have the link already, right? So this is the notebook that I'm trying, I will see, right? We are not going to go into it. The main thing is just to show you that you can import the library. You can, I start running Shift Enter. You can define, for example, I say I want to design a chip with a chip size of 5 millimeter by 5 millimeter. I define the variables, right? I define the length of the resonator. I decide the launch pad, etc. Right? So let me just go all the way to the end because it's not my intention to discuss the detail. Yes. So now, it failed the crash. So this is one problem. So let me do it again. Kernel.
Okay, that works.
So this, yeah, anyway. I need to fast just to run it first. So you may run into this problem. But again, I show you the link to my video, and also you can go to Qiskit tutorial. They have a lot of good example. Of course, ours is modified from theirs, right? So now look at this. From scratch, it generates the whole circuit for us, right? Of course, we need to keep testing until we get the right thing. You see that this is a launch pad. And then this is a coplanar waveguide, a transmission line. Now, if I zoom in, this is the transmission line. Let me zoom more, right? You don't see this here, but when you generate the GDS, this will be the superconducting metal. And then this is also the metal, and this is the gap. So let me show you what it means. Yeah, so let's say this is the transmission line, right? So this is the GDS it generated. You have the gap. If you do a cut in AA, you see that these are the niobium superconducting metal. And then these are edge away space. And then the middle is the signal, and then space, and then ground plane. Okay, so ground plane is everywhere. That's the first thing. Second thing is, this transmission, just like for reading, if I have a signal come in, then it will go all the way to the right. But you see that here is inductively, we can capacitively, but in this design, it's inductively coupled to a resonator. Why I say it's inductively? Because you see that this is conductive plane. All this white part, it has not rendered yet. Eventually, it will be also the metal. So this is the metal connected to metal. So it's grounded. So there's no voltage signal, but it has a lot of current. So it's inductively coupled to the coplanar waveguide. So what? Now, if you inductively couple to this, then this is a resonator. You design it so that you have the right resonance frequency. For example, in this case, right, we design it so that the length is lambda over 4. So that lambda means the length of this resonator equals to the wavelength divided by 4. And because it's inductively coupled at one side, so it's shorter. And I did not tell you that at the other end, here, it is capacitively coupled to the qubit transmon. So lambda overall is the first mode that it can have, right? Just like the guitar string, right? But guitar string, both sides are actually fixed, right? Now it's lambda over 4. So that's first thing, right? So that's how you design it. Another thing is about the transmon. So there are many ways to design it, right? Also, what I'm showing you is not the final one or the best one, but we can see a little bit thing here. Here it's just a placeholder. We have not put the Josephson junction yet, right? When we tape out the GDS, we will then put the foundry's layout. They will provide us the layout of their Josephson junction, or they will put it for us. We just say that I'll put it here, and we tell them what Josephson inductance we want. So you see, this is a big cap, right? And then here is also ground plane. So basically, we form a big capacitance here. So that's why this is a transmon, because I have a Josephson junction and it's in shunt with a capacitor, right? So, yeah. Just for layout, it is not. I will explain more later. Yeah. So So he's saying that it's not a part of this layout. At this point, it is not. But actually, a little bit. Let me talk about that. But anyway, this is a Josephson transmon, and it's capacitively coupled to this resonator. So we can also use this one to manipulate the qubit. Now, for example, in this particular case, we actually share 2 qubits using one single coplanar waveguide. Now, we can use it to read the states of the qubit, we also can use this to manipulate the qubit through this resonator capacitively. On the left, of course, we need to design them so they have different qubit frequency. So this is a little bit like frequency multiplexing, but not at the same time. It just, we can selectively adjust that. On the left, I want to show this is because you see we have placeholder to put two Josephson junction. That is because we want to make a flux tunable qubit. So I told you earlier, the flux tunable qubit is by putting two Josephson junctions together to form a loop. And this is the area of the loop. So go back to your question. The only thing that we Qiskit method, up to this state now is that we need to decide how large the loop is because it determines how much flux we can go through, right? And we couple it to this 9, and this is the flux 9. When we want to tune it, we will apply a current to here. And if you look at here, again, this goes to the ground. So the current, you keep flowing, and you can imagine the magnetic field will go around so that I have lots of flux going to there. So by changing the strength of the current and the duration, then I can change, the strength of the current will change the frequency. So I can bring them together. And for the right time, then I can make an ice swap gate. But here is not, of course, be careful. I did not couple them. So these are actually two separate qubits. I did not show that. If I want to make it a 2-qubit coupling, I need to add a capacitor to couple them together. Then it is a 2-qubit gate. Again, a very hand-waving discussion. But this is the first thing regarding the Qiskit method, right? So it helps us to generate the layout easily, and you can just modify it. If you find something wrong, regenerate. And these are very common tools being used, right? So I already explained all the components here. Yeah. Yeah. They do. They do. No. This one is just for layout. We have not done the simulation. I will talk about simulation. Here is instead of manually laying out, you use this script to help you to lay out a big chip, for example, right? So now, then our goal is that when you want to design a circuit, for example, I want to design this 1-qubit gate. There are a few criteria I want to do. Remember, I want to make it a Transmon. So I want to make the, I guess I have typo. It should be EJ over EC larger than 50. Sorry. We want to make the Josephson energy much larger than EC, right? So this is a typo. Should be larger than 50. We also want to make the enharmonicity at least 10% of the qubit energy, right? It means that E21 minus E10 better to have 10% of E10, right? Now, this one I did not discuss. It's worth to mention a little bit, also almost time's up. It is that so far, if you remember all the current I showed you about the Josephson junction, it depends on something called IC, the critical current. This is the current above which you will lose the superconductivity of a Josephson junction. You cannot put a too big current to it. Then it becomes non-superconducting and it won't work anymore. This critical current is going to affect many designs, including Josephson's energy, you see here, IC, and then you determine the qubit energy. It also is going to affect other things. But when you fabricate a Josephson junction, you don't want to always measure it at low temperature because it takes long time and expensive. And turn out there's a relationship between its normal state resistance because it's just a capacitor with tunneling, which is Rn. This Rn times the critical current equal to some constant. So the foundry will tell you the normal state resistance of the Josephson junction you are going to measure. And you based on that, you determine what the critical current is. And with that, then you can design all the capacitor. For example, if you have certain alpha enharmonicity, then you just change your capacitor accordingly. If you need a certain qubit frequency, you change your capacitive energy and Josephson energy, also the critical current accordingly. Okay. Bina, we discussed that already. Then the last thing is this. Now, you was asking then, what do we need simulation? Yes, we definitely need simulation. The second part of this script is that now with this thing, we created the layout. We will then call a tool called HFSS. Instead of manually drawing your layout on HFSS, which is a microwave simulator, it will now then call the tool and then perform the simulation. It takes time to load it. But while you're loading, let me just have the final few words. First, you draw it, and then it's going to, we will just assume the Josephson junction has the Josephson inductance that we want. Now you see that the whole game is all about having Josephson junction as a nonlinear inductor. So we don't need to do any quantum mechanical simulation, right? All we need to do is just to assume that it has a certain inductor. Then we can do the circuit simulation. Now you see that it just rendered the structure we have drawn here very nicely. It takes maybe 1 minute to render. And then you will start doing simulation. What does it do in this command? We ask it to find the eigenfrequency and also the Q factor of the circuit. The eigenfrequency will give us the qubit mode, the resonator mode, etc., so that we can make sure that what we are designing meets the spec we have. Because again, remember, for example here, the G, the coupling factor of the 2-qubit gate, it depends on the resonant frequency of the 2-qubit. And that resonant frequency can be simulated where it is simulating now, right? I can do this. I can results, create a plot, and then ask it to plot the frequency, right? As at the passes. Passes is like it try to converge. I'm trying to simulate 4 mode of frequency. It only finished 2, but you gradually see that it has 4 mode. I have 4 important parts. If you look at this structure, I have a 2-qubit, 2 resonator, right? So I actually can try to see where they are based on this. So for example, just give me 1 more minute. I know it is 2:30 already, right? So I'm going to just right click. I will ask you to plot the field, the electric field on the structure. And you will keep updating, right? Because you still don't have the right result, so it's still a little bit noisy. But you see that the first mode is this qubit. And I can ask it to plot the second mode. I go to analysis, field, edit source. Right. So instead of plotting the first mode, I ask it to plot the second mode. Then I see the second mode is on another qubit, right? And maybe I can just one more demonstration, ask it to plot the third mode. And you see that it's at the resonator, right? So it is not converged yet. So that's why it is not very nice, but it gradually converges. Now here that you can go back, you say, hey, this is not the frequency I want. Then you go back to redo your layouts and simulate again. And eventually you need experimental verification. Finally, getting this useful, but there's one thing even more useful is that people have developed something called energy participation ratio, or something called BBQ, black box quantization. We just need to do this classical simulation And this classical simulation will tell us how the energy participates in different components. They came up with a theory and tell us that you can find the cross-cut. What is cross-cut again? Is how much you shift the resonator frequency for readout. It can also calculate the enharmonicity. So you just do this classical simulation. You already know what the cross-cut is, what the enharmonicity is. Then you can design your quantum chip already. And that's why I say you don't need quantum mechanics. Everything is purely classical at this stage. But we assume they do the right thing. Yeah, and I do have a video on how to do installation of this, do the EPR. And I think we will just conclude here. That's all we have. Maybe we can take, question?
Actually, what's your favorite way on how to simulate superconductor initial process? So I think you run eigenmode simulation assuming the superconductor. Yes.
Yeah, so we don't really simulate superconductor. We just make it as a perfect electric boundary condition. Yeah, and that's it. We did not even, okay, so now it's Q&A, so I can spend more time. Feel free to leave you if you're in rush. But I want to show you this. In principle, right, you want to simulate the Josephson junction. So here we have a Josephson junction here. In principle, you want to simulate it. But actually, we did not. What we did is just add a boundary condition to it. Yeah, exactly. Right? We define an inductance here with a variable. And that's it. We just make a boundary. Say, oh, here I have a 10 narrow Henry inductor. So that's it. Yeah.
But in general, like you should have simulated superconductors, yes, for the superconductor, because they don't do like conductance for the readout resonator all the time.
We don't. We just make it a perfect conductor because they, No, kinetic intense is you mean for the Josephson junction or for others?
Well, yeah, like for the resonator. So this is what the way you present it. Yes.
Yeah, maybe it's not large. Yeah, I have not heard of people doing that. Yeah, you only just simulate geometric inductance. Yeah.
It's like deep dive of the originator.
The metal is niobium usually. Yeah, but it's superconducting state. Yeah.
I'm also doing a different way, like either like the circuit impedance, but there's like frequency dependent, you can see target more so or it was like complex dielectric wave is real and measuring part of the real model.
Yeah.
So when you're trying to decide the Josephson quality of your readout circuits, your control circuits, and you have this this circuit with its own noise components, at least maybe fragment conditions. Then you have the qubits, they have their own variation, and they're not ideal either. So how do you both of them you're kind of looking at the performance of the combined system. Do you have any suggestions for how you partition like? Am I being limited by my qubits, or is it my problems with control electronics? I think this sort of partition, how to do.
Here you go ahead. Yeah, here is no.
Now for the readout and detectors and then I can calculate the readout. Yeah.
Indeed, now, okay, if for superconducting qubit, the calibration is very important. So they spend a lot of time calibrating, first classify 0 and 1, particularly some of the state can go to 2. So you want to do that of calibration. And then they come up with a confusion matrix to, confusion is like you know you put in 0 and 1, right? And then you correct what you have done. And then use that one to make the readout more accurate. Yeah, so calibration is important. Okay, any other questions? Yeah.
Kind of a naive question. For your CPW, for the readout resonator, you define the length to the edge of the ground plane that hole that the qubit is sitting in?
You mean this part, the resonator or the CPW?
CPW.
This one?
Another
Oh, here. Okay, here is another important thing is how long you want it overlap depends on the quality factor you're looking for. So you should not have a very low quality, high quality factor because then it means you take a long time to read, right? If you make it small, usually we make it about 5,000 to 10,000, and that will give a reasonable readout time, right? Because if you don't interact, you can never read anything. But if you have too much interact, your qubit can lose information out to outside very fast. So you design it by the Q. Yeah, usually that's what you do.
part that extends to area with qubits.
Oh, this one? Yes, yeah. We try to do this. Again, number 4 is not exact, it's just like theory, right? So yeah, we go from here to here. And then after that, we do simulation to verify that it does oscillate at that frequency. Yeah. But yes, we include from all the way from here to here. Okay. That will still stay for a little bit longer if you want to discuss. Yeah.